Good afternoon, everyone. Welcome to another Atom seminar. Today we have the pleasure to welcome Pedro Velho, a Ph.D. candidate specializing in thermodynamics at the University of Porto. Pedro earned his master's degree in chemical engineering from the University of Porto in 2020, conducting his thesis on development of a more predictive CPA equation of state at the Technical University of Denmark, where he continues to collaborate. And Pedro's research focuses on phase equilibria, equation of state, green novel solvents, and thermodynamic modeling of electrolyte-containing systems. And currently, he holds a prestigious doctoral grant from the Foundation of Science and Technology and serves as the only European non-doctorate member on the early career board of the Journal of Chemical and Engineering Data. Pedro's contributions to the thermodynamics field are substantial and impactful. So welcome again, Pedro. Please feel free to start your presentation.
So thanks, Larissa, once again for the introduction. Obviously, I have to thank you all for the invitation to be here today. My name is Pedro Velho. I'm a PhD candidate at the University of Porto under the supervision of Professor Eugenia Macedo. And today I will talk about green ionic liquids, or at least greener ionic liquids. So this presentation is titled In the Search for Greener Ionic Liquids from Synthesis to Application. And throughout the presentation, I will talk about our most recent paper. So let's say 5 years from now. And then let's see what we have been doing here at Porto. So I'll start this presentation by commenting on the diversity of ionic liquids, and then I'll move on to choline amino acid ionic liquids, which are the most promising ionic liquids, giving you some basic concepts on their synthesis, on their thermophysical characterization, and then we'll move on to ionicity determination, which is a very important property concerning ionic liquids, and also to ionicity prediction using thermodynamic modeling. Then in this second part of the presentation, I'll delve into vapor pressure osmometry, which can provide very important information concerning solid-solvent interactions for ionic liquids. And then I'll finish the presentation with some insights into liquid-liquid equilibrium determinations for aqueous two-phase systems, insights into extractions using aqueous two-phase systems, and also in the immobilization of the target species that we are extracting using aqueous two-phase systems based on green ionic liquids. So as you all know, ionic liquids or molten salts are defined as salts with a melting point below 100 degrees C at atmospheric pressure. Nevertheless, this salt characteristic or this salt definition is relatively broad. So a lot of different distinct chemicals exist in this chemical family. So this definition is too broad, so we have too many different properties and too many chemical compounds. So we cannot say that an ionic liquid, just because it is an ionic liquid, it's green. So when we are looking for a green ionic liquid, we want it to have a high solubility in water, to be highly biodegradable, to present negligible volatility, and to have a low toxicity. And in fact, some years ago, when everyone was starting to study ionic liquids, they were touted as revolutionary. Everyone thought that they were going to change the world. And some years later, actually, they didn't, just because some of them, or a huge fraction of them, is not that green. And this takes us to choline amino acid ionic liquids, which are often regarded as the most promising and secure ionic liquids. They present lower toxicity, higher biocompatibility, and biodegradability. They have an easier chemical synthesis, and they have abundant raw materials. Choline amino acid ionic liquids, as the name suggests, they are composed of choline, which is an essential nutrient that you can find in eggs, in apples, or in fish, for example. And they are also composed of amino acids, which are the building blocks of proteins. Some common choline amino acid ionic liquids include choline alaninate from alanine, choline glycinate from glycine, choline leucinate from leucine, choline serinate from serine, and colinium threonate from threonine. And throughout this presentation, you'll see always these abbreviations because it's easier to understand the ionic liquid we are talking about. So, in the synthesis of choline amino acid ionic liquids, the first step is choosing the precursors. Normally, they are an amino acid salt and a choline salt, such as choline chloride or choline hydroxide. Normally, choline hydroxide is way more expensive than choline chloride, so in our research group, we normally use choline chloride in our synthesis. In the first step of the reaction, we start by the amino acid. In this case, it's glycine that is shown here. We react the amino acid with potassium hydroxide until we obtain the amino acid salt and water. This takes about 3 hours, for which it is I would say, rather fast reaction. Afterwards, in the second step, which takes approximately 12 hours, we react the amino acid salt with choline chloride to obtain the ionic liquid and potassium chloride. All these reactions are performed in ethanol, so not in water, and this allows us to remove potassium chloride from the solution using filtration under vacuum at the end of the reaction. Afterwards, so as to be sure that we are rid of all volatile components, we take this solution to a rotary evaporator for about 3 days, so we finally have the pure ionic liquid. Now, we have completed our ionic liquid, we have synthesized it, but we have to be sure that the chemical structure coincides or is the same that we really want to have. So in order to validate chemical synthesis, what we can do, for example, first of all, is to check liquid density, so as to be sure that there is no contamination from water or from ethanol. But if you really want to understand if the structure is correct, you have to, for example, analyze the Fourier transform infrared spectra or the nuclear magnetic resonance spectra. Nuclear magnetic resonance has the advantage of understanding the bonds between the atoms, so you can actually understand if the bonds are correct. Nevertheless, in our group, it is more common to analyze the Fourier transform infrared, which in turn allows you to understand which groups exist in the synthesized ionic liquid. As you can see here, we have the Fourier transform infrared spectra for choline alanine, choline glycine, and choline serine. You can see all the spectra here, and obviously a lot of the peaks are common, such as this one here, which comes from choline and has a larger intensity for serine, as you can see here. Normally, they also present these two peaks here, which are due to the carboxylic groups, and this, which is due to the NH2 group. Nevertheless, after having validated the chemical structure using Fourier transform infrared spectra, we can also do some computational chemistry. So computational chemistry may provide us an additional validation, and we can do so by predicting the IR spectra and comparing the IR spectra with the FTIR spectra. As you know, density functional theory has many pros, such as being an ab initio simulation method, so no experimental input is required, but it also has some cons. For example, it has a practical limit of 500 atoms, and we can only compare peak location and relative intensity between an IR spectra and an FTR spectra. In our group, we predict IR spectra, infrared spectra, normally by combining the B3-lib hybrid functional with the 6311++ GD basis set in an effort to try to decrease experimentation. For example, here you can see a particular case in which we had a mixture of choline citrate and choline salicylate. So this one is an ionic liquid with pharmaceutical activity, and here you have pretty much an organic salt. And here you can see their separate spectrum. So you can see the spectrum of each chemical in pure state. And here you can see the experimental Fourier transform infrared spectra. And as you can see, this is a binary mixture 1 to 11. And you can see that the experimental spectrum is pretty much a ponderated average or a weighted average of the spectra in pure state. And these will one day, let's say, to avoid measuring so many spectra and to have to perform so many experimental validations for the spectra and to compare them right away with computational chemistry, avoiding NMR measurements, for example. Now, after having validated our ionic liquid, we need to understand its thermophysical properties, since its final application will heavily depend upon its properties. And the most common properties that we analyze in our group are liquid density, dynamic viscosity, refractive index, and electrical conductivity. We do that for ionic liquids in pure state and ionic liquids, for example, in binary mixtures with some solvents, such as water, ethanol, or propanol, which are normally the most common. Here, for example, you can see liquid density for choline laninate with water, with ethanol, and with propanol. And as you were expecting, density in mixtures with water is way larger than the ones having alcohols. But a very interesting thing happens here. That is, ethanol is actually less dense than propanol in pure state, but in the mixtures, actually it becomes denser than in the mixtures with which have an ionic liquid and propanol. And this is probably due to the increased polarity of ethanol, which more effectively solvates the ionic liquid, which leads to a decrease in volume and an increase in density. On the other hand, you can see here the dynamic viscosities of choline laninate with water and choline laninate with ethanol. And as you can see here, as we were expecting, with temperature, viscosity decreases a lot. And with an increase in the ionic liquid mole fraction, we see an exponential increase in the viscosity of the mixture. With ethanol, actually found out that the viscosities were not that different. Obviously, they were a bit lower, but they were pretty much very close to the ones obtained with water. Other very important property when we are talking about ionic liquids or electrolytes in general is electrical conductivity. And normally we measure electrical conductivity, obviously, and then we also calculate the molar conductivity. As you can see here in this example, also for the same choline amino acid ionic liquid with the same solvents, you can see that normally they present these maximum at about 0.1 or 0.2 mole fraction of ionic liquid. And this is due to the existence of a sweet point, pretty much, in which you have a good number of charge carriers, but you also have space for all the charges to circulate. So you don't have too many charges, which could, in fact, hamper the dislocation, the movement of the charges. And as you can see, in water, conductivity is way larger than in ethanol and then in propanol, which actually agrees with their polarities or the electric constants. Normally, when we are talking about molar conductivities, what happens is that you don't see that maxima. It's generally just a decrease because all the molecules of ionic liquid that you start adding to increase concentration, let's think this way, start contributing less and less to the overall conductivity since they cannot move that much since you have a decrease in the available space. Other very important property, normally to assess the purity of ionic liquids in pure state, is refractive index, which is generally coupled with liquid density to assess the purity. In this case, we did some measurements for choline amino acid ionic liquids with some solvents such as water. And here you can see choline threonate and choline glutamate in water. And as you can see, the refractive index for glutamate is way larger than for threonate, and that is due to the increasing, to the larger polarity of glutamate compared to threonate. As you can see here, glutamate has two carboxyl groups, carboxylic acid groups, which obviously increase polarity, and obviously this causes a larger refractive index. Now, we arrive to a very important property which is often ignored in ionic liquids, which is ionicity, or dissociation extent or degree of dissociation of ionic liquids. They all mean the same. And pretty much ionicity refers to the fraction of the ionic liquid molecules which are dissociated into their constituent ions. So let's say they say the percentage of the molecules that are divided into cation and anion. And we can estimate ionicity using the Walden plot methodology. So we plot the logarithm of molar electrical conductivity and the logarithm of the inverse dynamic viscosity. And pretty much we have the point here, for example, this is for pure choline alaninate, and we measure this distance to a reference line, which is given by potassium chloride, an aqueous solution of 0.01 mole per liter. And this distance, normally known as delta W, allows you to estimate ionicity. So ionicity will be given by 10 to the power minus this distance. And for pure choline alaninate, it is about 21%. So this is a very intriguing fact. It means that the ionic liquid, even though it is in pure state, it is comprised of a solvent and ions. So the ionic liquid is solvating itself. You do not have a neutral molecule. You have a solvent and a cation and an anion coexisting, and 21% of the molecules are actually dissociated. The Walden plot methodology also allows to class ionic liquids as good, poor, or non-ionic, but this is a very rough qualitative assessment of their ionicity. So I advise you just to stay with the quantitative part of it and not the qualitative evaluation. Obviously, if the ionic liquid pure itself alone can be dissociated, the same happens in binary mixtures. So pretty much doing the same analysis, so representing a binary mixture of choline threonate in water and choline glutamate in water, you can see here all the points in the Walden plot, and the closer the points are to the reference line, the more dissociated the ionic liquid is. And if we take a look at this plot here, in which you have IL ionicity and the mole fraction of ionic liquid, we can see that choline glutamate is actually more dissociated than choline threonate, and this is due to the larger polarity of the glutamate ion compared to threonate ion. So since water is a polar solvent, it more easily solvates glutamate compared to threonate. And actually, this result is very funny. So pretty much when you can see that this ionicity is not constant, mostly for choline glutamate, it changes a lot. So depending on composition, we have a variable ionicity, which obviously will change our thermophysical properties and cause pretty much an unpredictable effect on the ideality of the mixture. So as some of you may remember, I presented something related to this in Equifaz in Campinas some years ago. And actually, we can model or predict ionicity using thermodynamic modeling. In our group, what we do is couple the universal quasi-chemical model, which accounts for short-range interactions, so interactions between neutral particles, with the Pizza-Debye-Huckel equation, which accounts for long-range interactions, so interactions between charged species. Pretty much, this allows us to avoid experimentation and to right away predict ionicity. So how do we do that? Pretty much, we'll start by taking solubility data from literature. Then we take these values as maxima, so as boundaries, for iterating a composition of ionic liquid in solubility data. Then we start iterating values of ionicity, and we do so repeating and repeating a lot of times until we finally describe solubility data the possible way we can, pretty much still respecting the isoactivity criterion. And this allows you to estimate the degree of dissociation for ionic liquids in binary mixtures just based on solubility data. Now, as I mentioned, the presence of ionic liquids in binary solutions, for example, have an unpredictable effect on the ideality of the mixture, since ionicity heavily depends on the ionic liquid and on the solvents present. Therefore, in our group, to help with this matter, what we do is use vapor pressure osmometry. Pretty much in a vapor pressure osmometer, we have a glass cell, which is saturated with solvent vapor, let's think water. So pretty much we add 10 grams of liquid water to the chamber, then it starts to evaporate, and then it completely saturates the chamber. There, you have two thermistors, so they measure temperature. On the left one, thermistor number 1, we place a pure drop of solvent. On the other, we place a drop of a binary solution of an electrolyte. So in the same solvent, but with an electrolyte. What happens is that the presence of the electrolyte causes a decrease in the vapor pressure. Therefore, in this drop, we have a smaller vapor pressure. So what happens is that the solvent starts to condensate in this thermistor, increasing temperature. The osmometer then records the difference in temperature, which is converted to a resistance or to a signal in the Wheatstone bridge. And then we can use this difference of resistance, the delta R, to calculate the osmotic coefficients, which allow us to relate which is the osmotic pressure of the solution with the osmotic pressure in the ideal case. With the osmotic coefficients, we can calculate activities, and with activities, we can calculate pressure. Pretty much, we can determine the vapor pressure of the solution here. And as you know, in a lot of different excess Gibbs free energy models and equations of state, we really need vapor pressure to tune our models. That's why liquid density of binaries and the pure components and the vapor pressure of solutions is really important for thermodynamic modeling of electrolyte containing systems and mixed solvent systems with electrolytes. So as you can see here, the presence of an electrolyte, here you have the molality of the electrolyte, here you have the decrease in pressure, and the presence of an electrolyte causes a decrease in pressure, as you can see here. These results concern some organic salts. They are not for ionic liquids, and this is due because when we are, for example, studying an aqueous two-phase system, we have the ionic liquid, we have the solvent, but we also have the salt. For example, an organic salt or an organic salt. So as to properly model all the interactions that exist in a system, we have to do all these for the ionic liquid and for the salt, since they are all electrolytes. So these are the calculated, the experimental determined osmotic coefficients. And as you can see, they are pretty much all below unity, which means that there are strong interactions between the solid and the solvent. Moreover, you can see that normally sodium salts present a lower value for the osmotic coefficients, and that may be caused by an enhanced polarity for potassium salts, which allows water to solvate these type of salts better. Now, since we love putting together some experimental data and thermodynamic modeling, we also model the osmotic coefficients, and normally we do that with the extended pizza model of Vacha. So some years ago, Pizza combined the third order virial expansion of excess Gibbs free energy with a Debye-Huckel term. And this model was later modified by Archer, which included a dependence on ionic strength in this term here, pretty much adding the C1 exponential to this factor here. And this is to better describe interaction at larger concentrations of electrolyte and also when in the presence of ion pairing. This model, so after having modeled our osmotic coefficients, or if you prefer, after having correlated these osmotic coefficients, we can also predict the mean mole activity coefficients and the excess Gibbs free energies. Mean mole activity coefficients, as you know, are very important for a huge number of thermodynamic models, while excess Gibbs free energies allow you to better understand the interactions between solute and solvent. And the equations are pretty much analogous to the ones used for the osmotic coefficients, with some modifications happening in these terms. Now, concerning GE, it is easily determined pretty much having in mind the stoichiometric coefficients, molality, the mean molar activity coefficients, and the osmotic coefficients. So, and here are some results for the same salts that I've shown you before. And as you can see here, pretty much sodium salts have a very constant and low mean molar activity coefficient, while potassium salts have an increasing value for this parameter, having more or less an ideal solution at around here, or close to ideal behavior, let's say, in this zone, but then they start to present a positive deviation. Concerning the excess Gibbs free energies, these salts, normally composed of sodium or sodium and potassium, they have a negative value for GE. And this means that interaction between solid and solvent is favorable. So we may expect the solvent to accurately solubilize the salt. On the other hand, here for potassium salts, we have positive values for the excess Gibbs free energies. And this means that the interaction between the solvent and the solid starts to become repulsive. By having a positive value, it doesn't mean that the salt will precipitate right away. It just means that some repulsive interactions are starting to arise. And if we keep on increasing molality of salt, this value keeps on becoming more and more positive, becoming more and more intense, then immiscibility will happen, or let's say precipitation of the salt. Now, as I mentioned you, we normally couple ionic liquids with salts in aqueous two-phase systems, which pretty much consist in a liquid-liquid extraction technique in which two water-soluble components enrich to, let's say, immiscible phases. So, for example, we have an ionic liquid, which is soluble in water, but we also have an organic salt, which is soluble in water. But what happens is water will preferentially solvate one of the components and leaving the other behind, so causing immiscibility. This component that causes an immiscibility is called the salting out agent. And in aqueous two-phase systems based on choline amino acid ionic liquids, normally it is an inorganic salt. So in order to determine the aqueous two-phase systems, normally we have three different steps. We start by determining the solubility curve. And we do so with the cloud point methodology. So pretty much we titrate as an aqueous solution of one of the components using an aqueous solution of another component. So we have, for example, an aqueous solution of one component, we start adding the other one until we see some cloudiness. So we see some eagerness to change to the appearance of another phase. Then we add water, and then we add some extra component too, and we do so repeating and repeating until we accurately describe the solubility curves. Here you have just 4 examples of different solubility curves of some systems. After doing so, we can correlate the solubility data using, for example, the well-known Marchuk equation or other empirical models. Afterwards, what we do is characterize the homogeneous zone. So the zone in which you have one single liquid phase. For example, below this red line, squares here, you can see that this is the homogeneous zone. And what we do is, in several different binary and ternary points, what we do is to measure, for example, conductivity, liquid density, or refractive indices. And they have to be independent properties. Normally, we measure 2 different properties. And what we do is to measure properties in this homogeneous zone and to adjust third-degree polynomials to these thermophysical properties, which we will later use to determine phase composition. So pretty much in the third part of liquid-liquid equilibrium determinations, what we do is we start with mixtures in the immiscible or heterogeneous zone, the gray circles here, and obviously we know that this composition does not exist. So these points here will separate into top and bottom phases. We do so, we let them settle for about 12 hours, and after settling, we separate the top and the bottom phases, and we measure the same properties that we measured here. Then we pretty much what we do is to intercept the planes defined by the polynomials. Pretty much when intersect two planes, you obtain a line. Afterwards, we use the mass balance to find the point in which our composition is defined. Pretty much we do that to determine the top phase and the bottom phase compositions of each mixture. When I say doing the mass balance, is not forcing compositions to be in the binodal curve. It's just remembering how much polymer or ionic liquid we added, how much salt, how much water, and just to be sure that the final total masses of each compound correspond to the initial ones. And as I said, this is called the binodal curve, not to be mixed with solubility curve. The solubility curve pretty much corresponds to the line that connects solubility data, while the binodal curve connects tile line data, and pretty much they will be the same if experimental error is zero, but obviously it is never zero. So in my opinion, they should always be kept separately, and they correspond to two very different things. So after having all this work and having determined aqueous two-phase systems, we know the solubility curves, we know the binodal curves, we know the composition of all phases, then we can use them to extract, for example, vitamins. As you can see here, we have the choline, a laninate, and with an organic salt, and with water. And as you can see here, we are pretty much separating cyanocobalamin or vitamin B12. And you can see that the top phase, which is rich in ionic liquid, is actually very selective towards this vitamin. Sadly, aqueous two-phase systems based on green ionic liquids, such as the ones of choline amino acid ionic liquids, they normally present small immiscible liquid plus liquid zones. So normally for an ATPase based on polymers, you'll have 6 or 7 tie lines. But for these kind of systems, normally you have 3, 4, 2, and even this area here is normally very small, and this may be a struggle for some separations. So as you probably figured out already, in our group, when we are dealing with aqueous two-phase systems, we extract normally either biomolecules or active pharmaceutical ingredients. Biomolecules could be antioxidants, vitamins, proteins, pigments, sugars. Active pharmaceutical ingredients normally are antipyretics or antibiotics, anti-inflammatories. And now, quite recently, we have been focused on active pharmaceutical ingredients since they are pretty much polluting our waters, as you can see here in this small image. So active pharmaceutical ingredients are a class of emerging pollutants, and they are mainly originated from hospital or household effluents. They are known to pose a profound consequence to aquatic environments, and we need to find ways of extracting these contaminants from water, since they end up in rivers and in oceans due to an improper treatment of these contaminants. So here in this plot, you can see pretty much the results for the extraction of acetaminophen or paracetamol, which is an antipyretic, and amoxicillin, which is an antibiotic, using aqueous two-phase systems based on choline amino acid ionic liquids. And as you can see here you have the natural logarithm of the partition coefficients, so of the ratio of concentration of this API in the top and in the bottom phase. And here you can see that amoxicillin, for example, was really well extracted using these systems, for which choline amino acid ionic liquids could pose a very interesting way of extracting APIs from waters. Now, the problem with ionic liquids is rarely extraction. I mean, they are very good at extracting all the components that we test pretty much. The problem is, how do you get back what you are extracting? And the problem is selectivity. You want your ionic liquids to be selective to extract that specific biomolecule or to extract drugs, for example. So in our group, what we do is pretty much we have two different strategies. If we are talking about biomolecules such as vitamins or antioxidants, what we do is microencapsulation by spray drying, for example, using sodium alginate. So what we do is to microencapsulate the salt the choline amino acid ionic liquid, and the biomolecule. So we have an aqueous to phase system. We remove the top phase. The top phase is super concentrated in a biomolecule, and then we microencapsulate all these phases so as to, the final objective, to make dietary supplements which can be used to tackle hair loss or premature aging, taking advantage, for example, of the antioxidant activity of some compounds. Microencapsulating biomolecules ensures a predictable biomolecule release and also delays degradation by oxidation. On the other hand, when we are talking about active pharmaceutical ingredients, we synthesize an API-IL. So we synthesize ionic liquids based on active pharmaceutical ingredients, which preserve the pharmaceutical activity of the pharmaceutical components. So pretty much we take the top phase, then we can evaporate all the volatile components if we have them, for example, using a rotary evaporator, and then we we mobilize this pharmaceutical in an ionic liquid, which may allow you to apply these ionic liquids as topical delivery systems, for example, in agriculture, for cows, for example. We have a very interesting work in which we did that with salicylic acid. Pretty much we removed salicylic acid from water, then we immobilized it in an APIL, and the idea is to use it as a topical delivery system due to its anti-inflammatory activity. Obviously, immobilizing these pharmaceuticals always delays degradation. But I would say that the most important part concerning active pharmaceutical ingredients is not the final application of the residue, but is decreasing the amount of pollutant water. So we start with a pool of polluted water, and then we may end with pretty much a small vial of an API-IL, and we can recover all that water that was contaminated with a very insoluble in water. They are pretty much insoluble, and for example, antibiotics. So final highlights. As I hope you have understood, choline amino acid ionic liquids are the most promising and secure ionic liquids for destruction of labile species such as antioxidants, since they present lower toxicity, higher biocompatibility, and higher biodegradability. On the other hand, we are using computational chemistry to reduce experimentation and to better understand solid-solvent interactions. And we have some works, for example, in the determination of the non-randomness factors of biomolecules using just computational chemistry, which has been helping us parameterizing equations of state and GE models to better describe electrolyte-containing systems. Lastly, even though ATPS is based on choline amino acid ionic liquids generally present very small liquid-liquid areas, they provide extractive media with relatively low ionic strength and viscosity. Obviously, considering that they are ionic liquids, they are viscous, but they are not that much compared to other, for example, first-generation ionic liquids, and they safely allow to immobilize the target components either in microencapsulation or immobilization in ionic liquids. Now it's time to thank all entities which funded my research, to thank all my students, to thank my supervisor, Maria Eugênia Macedo, and obviously to thank you for your attention in the entire presentation. Thanks.